Okay, so in this video we are going to talk about exponential functions. And so we're going to do that by examining insects and how they multiply extremely quickly. I personally hate ants. I haven't had an ant attack in my home in a long time. But just let's say there was some ants in my backyard, and there was initially, let's say 20 ants. And ants multiply very quickly, and we're going to say they multiply at a rate. They can actually multiply their population by 3 times every single day. So we're gonna have a common ratio. It's called common ratio of 3, and we want to know how many ants are we going to have after 15 days if we leave it untreated. So we'll say the number of days is going to be 15 days, and we're wondering how many bugs or how many ants are we going to have. So we want to solve for some total question mark ants. And so what we can do is we can just set up a table. And so let's do that. Let's set up a table here, and actually I'll create some space so I got room. Actually, we'll just go to here. Okay, so this is going to be the number of days, and so this unit of measurement for this column is days. And then this is total, and this unit of measurement is going to be ants. And this is also going to be the same thing. T is just going to be our kind of final solution, but not split up into the different factors. And you'll see what I'm talking about in a sec. So we are starting with 20 ants. They get into my backyard, and no days have passed yet, so they just came in. So after 0 days, I've got 20 ants in the backyard. So obviously 20 goes into both of these columns. Now overnight they triple. So after 1 day, so 1 day has passed, and so I'm going to say, well, how many is that going to be? 20 times 3, and then that's going to be equal to how many ants? 60. So easy enough. So then we go to the second day, and then what's that going to be? Well, we have 60 ants, and we want to multiply that times 3, and then that's going to be 180 ants. But what we can do is we can actually look at it a slightly different way. 60 is the same thing as 20 times 3. So what I can do is I can actually replace this. Let me get rid of this 60. And then instead of writing 60 there, we're going to write 20 times 3, which is the same thing. So 20 times 3. We can all agree that 20 times 3 is 60, times 3, that's 180. So then we go to the third day, and we could do the same thing. I could say 180 times 3, whatever that is. But rather than doing that, I'm going to say 180 is the same thing as 20 times 3 times 3. So I'll write it that way. So 100 is the same thing as 20 times 3 times 3. So 20 times 3 times 3 is 180, and I'm multiplying that population after 2 days by another 3. And let's see what that value ends up being. So we have 180 times 3, and that is equal to 540. So this is 540. And we could keep going on and on, but you can kind of see a pattern here. Well, this doesn't have a 3 here, but this has a 3, and then this has 2 3s, and this is 3 3s. And as you can imagine, after 4 days, we're going to have 4 3s there. So what you can do is you can actually write this exponentially. This is actually 20 times 3 to the 0th power. And what's anything to the 0th power? It's 1. So 20 times 1 is 20. And this is 3 to the 1st power. So this is 20 times 3 to the 1st power. And then this is equal to 20 times 3 to the 2nd power. And then on the third day, after the third day, it's 20 times 3 to the 3rd power. Sorry, this looks like a, that looks like a 3 right there. So let's erase that and make sure that's a little more clear. So that is a 2. And so we could write this all out, but it's really not necessary at this point. So we'll know that after 4 days, it's 20 times 3, quantity of 3 to the 4th power. And then we can, again, go back to our calculator here, and we can say 20 times 3. And we're going to raise that to the 4th power. And then what do we get? 1620. That's a pretty big number. So it goes up really quickly, much faster than a linear equation, which is what we've been working to prior to this. So we want to see, well, how many ants are we going to have after 15 days? And you might think, well, it's probably going to be a lot because it's going up pretty quickly. So let's find out what that is. But before we do that, let's just get a general equation. So after n days, you could actually just say that n is equal to, well, after n days, t is equal to, 20 times 3, which is the common ratio. That's the common ratio is the amount that you multiply the initial amount by, raised to the power of n. And so then t is equal to 20 times 3 to the nth power. So our general equation would be t is equal to 20 times 3 to the nth power. And what is 20? Well, this is our start value, and then this is our common ratio. So really, the overall general equation, if it's all in variables, is going to be t is equal to f times the quantity of r raised to the nth power. And this is the kind of the form that I like. You'll often see it, this way: y is equal to a times r to maybe either the n or the x power. But I prefer this because it makes a little more sense. You have, t is the total amount at any given point after so many periods, and the periods in this case is defined by 1 period is 1 day, and then f is your start value, and r is, it makes sense to use that variable because that's your common ratio. So going back to this problem, we have n is equal to 15 days. So then we'd have 20 times the quantity of 3 raised to the 15th power, and then let's find out what that is. So we'll say that is 20 times the quantity of 3 raised to the 15th power. And you get a gigantic number. It is literally in the millions here. Let's see what this is. 286,978,140. So I know I won't remember that. But anyway, so this is right here. This is going to be 286 million. Let's see what that is again. 978,140. 978,140 bugs. And that's how many bugs you would have after 15 days if you started with 20 and they were increasing by, they were tripling at the end of each day.